So welcome to this quick session on laws of thermodynamics. It will be a short one. So remember, I've divided it into 5 topics which I find really are really important from the exam point of view. Supposed to understand them in detail. But the thing with this topic is the theory is very small, but the understanding is so deep that the problems tend to be very difficult. So I'll try my best to tell you what to study, but the fact is you have to have a really good theoretical grip on this topic, because it's not a lot of math, it's really a lot of understanding, a conceptual understanding as far as heat and thermodynamics are concerned. So coming to this, we'll start with the first law and try to understand how first law basically is a solution to about 80% of the problems in this topic, right. After that, we'll discuss a few basic thermodynamic processes, and in this I'll give you a very general, a very powerful formula with which you can actually play around with anything in the topic, and the rest of the 10% questions will be done by that, and 90% done. The other 10% questions will just combine of these three, either zeroth law, which is rarely asked, which is because it's very simple. Heat engine is a very simple topic. It has a very direct formula, and efficiency of a cycle is something which we'll look into. So let's proceed. So let's look at what first law is. So first law is very simple. It's written mathematically as delta Q is equals to delta U plus W. Delta Q is the heat supplied or taken out of the system. Delta U is the net internal energy change of the system. Remember, it's the change of internal energy. It's not absolute internal energy. I can never find out what absolute internal energy is in this problem, right? So that's what it is, and W is basically your work done. So let's look into detail into what each of these three terms are. So first, you should know the sign convention. If heat is given to the system, then delta Q is greater than 0. If heat is taken from the system, heat is removed, then delta Q has to be less than 0. If work is done by the system, that means the system expands. Work is done by the system, then W is greater than 0. If it is done on the system, then work done will have a negative sign. Similarly, delta U is the internal energy change. Remember, delta U depends only on temperature. Delta U depends only on temperature change. And delta U will be greater than 0 if temperature is increased. Delta U will be less than 0 if temperature is decreased. So delta U depends only on temperature, right? So we'll look into the formula of what these three are. So how it goes is you might have a beaker, right, filled with some gas, or you might have a graph, right? You might have a graph, some PV graph or a VT graph or any graph for that matter, right? You can have both these models. What they'll ask you is, if I add this much heat to the system, right, and the temperature increased by this much, then what will be the work done, right? Such questions will be asked. So simply you are supposed to put in heat with the appropriate sign. If heat is given to the system, you will put plus Q. If heat is taken from the system, you will put a minus Q, right? Whatever is given, you will put it with the appropriate sign in this formula. Similarly, delta U. If the temperature change is given, you have to use the formula for delta U is equals to NCV delta T. What is this CV? CV is the heat capacity for a constant volume process. Remember, there are different processes, right? There are different processes. There are infinite processes. What is a process basically? What is a process? The process is, if I give some heat to the system, how does the system respond? Does it use to increase its internal energy only and do no work? Does it use all the heat to do only work and no change in its internal energy? Does it use some amount of that heat to do work and also to increase internal energy? If so, will it use, if I give it 10 joules, will it use 9 joules to do 9 joules to increase its internal energy and 1 joule to do work, or will it use 8 joules to increase its internal energy and 2 joules to do work, or will it use 8.5 and 1.5 ratio? Like every ratio is basically a different process, right? That's why there are infinite processes. For that, first of all, you have to understand that. Out of that, one process is a constant volume process. A constant volume process, right? A constant volume process where your volume doesn't change at all, right? So I've actually started discussing different processes also alongside. So I'll discuss both of them together. So you need to know three formulas here. Q is equals to NC delta T, delta U is equals to NCV delta T, and VW is equals to integral PdV. These are the three formulas around which your entire chapter will just be played with. So how are these three formulas? How do you understand them? So first let's look at Q. Let's look at Q. If I have to relate Q to change in temperature, I need to find the C for that process. So C here is C here. So if I write Q is equals to NC delta T, C is for that process. C is for that process. That means if I talk about constant volume process, C will become CV. What is constant volume process? Where you're giving only heat, where everything is happening except the fact that the system's volume is changing. What is constant pressure process? There your C will become CP. Constant pressure process is everything is happening, everything might happen, but the pressure of the gas does not change, right? So CV. So basically delta U is always NCV delta T. Remember, delta U is always NCV delta T. Delta Q will be NC delta T. C is supposed to be found for the process, right? C is supposed to be found for that particular process, and the difference will automatically give you work. Or if you know the relation between volume and pressure, and you know final and initial volumes, you can actually use this formula, right? So there are a lot of ways you can use. They look three formulas, but from these formulas you can get some 15 more formulas for very specific cases, and you're supposed to use the specific case for a specific question, right? That is the challenge in this chapter, essentially. So how the problems will be is, you'll be given some PV graph. If I ask you V1 to V2, then remember area work done is integral PdV, right? So that means it is the area under PV graph. So this area will give you the work done, right? So basically you're supposed to subtract the heat work from the work from the heat, and then you'll get delta U, right? Or if you're given delta U and delta Q, they can ask you what is the work done. Or if delta U or the change in temperature is given, you can use this formula. If change in temperature is given, you can use this formula to calculate delta U. So if delta U is given and work is given, you can find out heat, right? So two will be given directly or indirectly, and the third will be asked for. That is how the problems will be as far as the first law is concerned. Coming to different processes, right? What is a constant volume process? Everything where like a process where everything can happen but your volume cannot change, right? So there your V is equal to constant, right? So delta V is equals to 0. If your delta V is equal to 0, then P delta V will be 0. So work done for a constant volume process is 0, right? Work done for a constant volume process is 0. So Q will straight away be equal to what do you say? Delta U, right? So Q is equals to NC delta T, remember? Always, but C is to be found for the process. This is a constant volume process, so it will be CV delta T, and Q is delta U. That is the reason why delta U will always be NCV delta T, right? Be it any process, delta U will always be NCV delta T, right? But Q will change according to the process. Coming to what is a constant pressure process. Constant pressure process is everything can happen, but your pressure cannot change, right? This is called as an isochoric process, and this is called as your isobaric process. So in an isobaric process, everything can happen but pressure can't change. So C will become Cp. So what will Q become? Q will become NCP, where N is the number of moles of the gas. Remember, everywhere here N is the number of moles of the gas, right? N is the number of moles of the gas. So Q is NCP delta T, right? NCP delta T. What is delta U? Delta U is NCV delta T, right? NCV delta T. So what will be the work done? Work done will be nothing but Q minus delta U, which is N into Cp minus Cv into delta T, right? So Cp minus Cv is taken to be R, right? Remember the value, remember this formula, Cp minus Cv is always R, right? So NR delta T is the work done. Or you could also use straight away this formula, right? How could you use this formula? This formula is always valid. PdV is always valid. This is not always valid because this is specific to this case, but P delta V is always valid for any process, right? This P delta V can be changed in different ways. I'll show you how I can derive this from this for a constant pressure process. So PV is equal to nRT, right? So PdV will be equal to nRdt, right? And because your pressure is constant here, I can bring it out of the integral. Because this is a constant pressure process, I can bring it out of the integral. So this is nothing but P into Vf integral dV, Vi to Vf, right? So Vf minus Vi is your work done, right? So P dV is P delta V is your work done, and I can relate that to change in temperature straight away because pressure is not changing but volume is changing, so temperature has to change, right? So P delta V can also be written as nR delta T. That is the reason why the work done here is nR delta T. So this was one process, right? For which I found C as Cp, and for this I found C as Cv, right? Now coming to two more processes, we'll discuss two more processes here. Let me make some space. So we've already discussed two processes. One is your isochoric where delta V is 0, and one is your isobaric where your delta P is 0, that means pressure is constant, right? And we are just playing around with three equations. First was your basically your first law, delta U plus W. Delta Q is equals to NC delta T, where C is different for different processes. Delta U is NCV delta T, which is the same for this. You will use the same formula for all processes with CV fixed for the gas. And delta Q, the thing with delta Q is you will use the same formula but your C will keep changing. But delta U, you will use the same formula without any change. You'll only take the values of initial and final temperature, and that's your delta U, right? And work done is integral P delta V, and we are just playing around with these three formulas, interchanging them. That's all that we are doing, right? So this was your first process, this is your second process. Let's discuss the third process now. For third process, basically this is your adiabatic process. For adiabatic process, it's very simple. What you're only supposed to know is your Q, delta Q is 0. That means there is no heat exchange with the surroundings. So if delta Q is 0, how will this equation modify? It will become delta U is equals to minus W. So work done will be minus of NCV delta T, right? That's all it will be. Remember, there's one more thing that I had to tell you. CV is given by this formula, R by gamma minus 1, and Cp is given by this formula, gamma R by gamma minus 1. What is gamma? Gamma is the adiabatic constant. So adiabatic adiabatic process is represented like this, PV par gamma equal to constant, right? And this is represented in a different manner, this one. This is PV power 0 equal to constant, because this is P is equals to constant, right? That's how it is. And similarly delta V also will be represented in some manner. So this is PV power gamma equal to constant, adiabatic process. This gamma is nothing but ratio of Cp and Cv, Cp by Cv, right? And Cp minus Cv is R, I already told you. Using this and this relation, I found out this, Cv is this, Cp is this. Remember the formula. So I can also write this as, I can also write delta U as nR by gamma minus 1 delta T instead of NCV delta T, because Cv is R by gamma minus 1. So I can also write this as W as minus nR by gamma minus 1 into delta T. Delta T is Tf minus Ti, always final minus initial, remember. So if I take this minus sign inside, it will become nR by gamma minus 1 into Ti minus Tf, right? So once again, don't think that this formula is invalid here. It is valid here, but I'm using the same formula in a different form here. That is the only thing. So remember, work done is done, delta Q is done, and this is done, right? This is what the process is. Coming to the fourth process now. Coming to the fourth, and because delta Q is 0, what is C for this process? Even if the temperature is changing, there is no heat involved, right? So what is C for this process? C for this is 0, right? I already told you C keeps changing for every process. So for this process, it was Cv. For this process, it was Cv. For this process, it's 0. Now coming to isothermal process. This is the fourth common process that we are supposed to know. In isothermal process, delta T is 0. Remember, the temperature does not change. So I'll use the first equation of motion. Now which term will become 0? Will I say Q becomes 0? I can't. Even though delta T will be 0, I can't say Q will become 0. I'll show you how. But can you say delta U will be 0? Delta U will be 0 because C keeps changing. Cv is fixed. Cv is fixed for a gas, N is fixed for a gas, delta T is 0, so delta U will be 0 for this process. But the question is, why will delta Q not be 0? Delta Q won't be 0 because C is not fixed for this process. What if this C is infinity? Then infinity into 0. Is it 0? No, I can't say. In fact, isothermal is not exactly delta T equal to 0. It is just that the temperature difference is very small, approximately 0, almost 0, right? Delta T is almost 0 and C is almost infinity. If C is almost infinity, then delta Q won't be 0, right? That is what the thing is here. So for this process, C is infinity. If C is infinity, if C is some finite value, then I will say delta Q is 0. But C for this isothermal process is infinity, and infinity into 0 can be some finite value. It's not 0, it's some finite value, right? If it is exactly 0, then I can't do anything. But this is an approximation. Isothermal process is an approximation where your delta T is approximately 0 and is very, very small. And C is very, very high. So high, something like 10,000 into 0.0001 is equal to some 10, right? So a very high value into very small value can be some finite value. That is the concept here, right? So delta Q, C is infinity, and that's why delta Q is simply your work done, right? And now I'll use work done formula. Like I can't evaluate delta Q directly, so I'll use work done to evaluate what delta Q is, because in this expression delta U became 0 and delta Q became W. I can't evaluate what delta Q is directly because C is infinity and delta T is 0, so I don't know what infinity into 0 is. I know it's some finite value, but I can't evaluate it directly, so I'll use work done now to evaluate, right? Here I used delta U to evaluate what work done is. Here I'll use work done to evaluate what delta Q is. So this is integral P dV, right? Vf to Vi. PV is equal to nRT, right? P is nRT by V. So because P is nRT by V, I'll just replace it here, and all my integral nRT by V dV, Vf to Vi. Now, can I take T out of the integral? Yes, because delta T is 0, temperature is same at all points, right? That is why I can take it out of the integral. If I was not able to take T out of this integral, I couldn't do this problem, right? I couldn't find I would have to find T as a function of volume again and then replace T as a function of volume, right? Because I can only afford to have one variable in this integral, right? And that's my V, right? Even if T was some function of V, then I would have to write that function here and then integrate it. But here I can take it out of this integral, and simply it is dV by V, Vi to Vf, and then I can say that work done. This was work done, right? So work done is nothing but nRT ln Vf by Vi, right? So work done, which is your heat, so delta Q is equals to work done is equals to nRT ln Vf by Vi, right? So you're supposed to remember this formula, you're supposed to remember how it has come. These are 4 basic processes. There can be infinite processes, right? So there is one very, very powerful, so for each of these you're supposed to know the PV graphs, the VT graphs, right? The PT graphs, all these graphs. In fact, for any process, if I give you the PV graph, you should be able to draw VT graph. If I give you VT graph, you should be able to draw PV graph. So if you understand these 4 processes, you can actually, if you understand these 3 graphs for these 4 processes, you can play around with all the graphs, right? That is my final call on this. So with this done, there's one more powerful formula that I would like to give you, right? This is the polytropic process. This is basically the combination of all formulas. If you have PV power x equals to constant, very, very important formula. If you have PV power x equals to constant, if your process is like this, x can be anything, right? If I put x equal to 0, it will become this process, right? If I put x equal to gamma, it will become this process. If I put x equal to 1, then it will become this process. It will become this process, isothermal process, right? Because for isothermal process, PV equal to constant, right? Because PV is equal to nRT, temperature is constant, so PV equal to constant. So x has to be 1 for this. In general, this equation represents all the processes. Every process will have its own x. So if I want the C for this process, what is the C? This is the C for delta Q. If I'm able to find C, I'll be able to find delta Q with change of temperature. So how do I find C for this process? How do I find the C is what is known as the heat capacity. How do I find the heat capacity for this? This is the formula. R by gamma minus 1 plus R by 1 minus X. Extremely important formula, this one, because this is used everywhere. So gamma is basically, if they'll give you that your gas is monoatomic, or your gas is diatomic, something like that. So for monoatomic, your gamma is nothing but 5 by 3. For diatomic, your value of gamma is 7 by 5, right? So mostly these 2 gases only they'll give you. Otherwise, you should memorize the gamma for different gases, and you're supposed to substitute gamma here. And if you know the process, if you know the x for the process, you can put that value of x and find the c and use the c here. Right? So for example, if I want what do you say, for constant pressure process, what is the C for the constant pressure process? For a constant pressure process, your x equal to 0, right? X equal to 0 because P is equals to constant. So if I want C for the constant pressure process, it's nothing but R by gamma minus 1. R by gamma minus 1 plus you will put x equal to 0 here because I'm talking about a constant pressure process here. So R, right, R by 1 minus 0 R, and this will give you gamma R by gamma minus 1, right? So C for a constant pressure process, which is Cp, is gamma R by gamma minus 1, and we already know it is that, right? So that is how you can put the value of x and calculate the C for a particular process, and you know where to use the C. Don't use the C here because delta V is always NCV delta T. You're supposed to use the C for this, right? So with this, we're done with discussing all the basic processes, and you're supposed to know the graphs for all the processes, all these 4 processes. That is something that you have to look into. Let's quickly wrap up the chapter. So let's understand how to find efficiency of a cycle, heat engine and refrigerator. So efficiency of a cycle, if a cycle is given to you, something like this, something like this process. I've drawn a Carnot cycle basically, but where these two are isotherms and these two are adiabats, but I'm not drawn it properly also. But the thing is, you might have any cycle on any graph. This is PV graph. You might have an NT graph, or you might have a TV graph or a PT graph. You can convert it to PV graph and use it the way you want. I'll tell you what the concept is. That is more important here. So if you have a process A, B, C, D, right? Remember, if you can convert any process to a PV graph, the area will give you work, right? Area will give you work. That is the advantage with working with PV graphs. You can straight away get work if you know the area. Otherwise, even if you are not able to convert, fine. You can calculate the work. If you want the net work, you can calculate the work done along AB separately, BC separately, CD separately, and DA separately, and add them, right? And more often than not, these branches will be one of the 4 processes that I told you before, right? So you're supposed to know the work done for all the 4 processes and apply the relevant formula to get the net work done, right? That's done. After that, you need to find out how much heat is given to the system. How much heat is given to the system? This is a very, very important part, because what students tend to do here is they tend to find the net heat of the process, net heat of the cyclic process, but that's wrong. That's wrong. Why? Why can I not use net heat? Because if you because the formula for efficiency is work done by heat given to the system. By heat given, remember, this is not net heat. This is not net heat. For example, in the process AB, I gave some heat Q1. In the process BC, I removed some heat Q2, right? In the process CD, also I removed some heat Q2, Q3. In DA, I gave in some heat Q4, right? So I'm not saying all of them are right also, but I'm just giving you a hypothetical example. I gave heat, I removed heat, I removed heat, I gave heat, right? So what will you consider out of these? What will be your Q given? Your Q given will be Q1 plus Q4 only. You don't even need to think about what Q2 and Q3 are, because what you will tend to do is you will tend to put net Q in this formula. You will tend to write Q1 plus Q4 minus Q2 plus Q3, and you will do the mistake of putting this in this formula, but that will give you the wrong answer, because efficiency is work done by heat given to the system, not the net heat exchange of the system, right? So you only calculate the processes, like for AB, you know one of the those 4 processes. These branches will mostly be one of those 4 processes, right? Even if it's not one of those 4 processes, if it's some PV bar x equal to constant, for this also I gave you the formula how to find C using x. So use the C, use delta T, right? Use delta T and find out heat for the process. Take only those heats where the value is positive. So for here, for example here, Q1 is plus Q1, right? Plus Q1. Q4 is plus Q2. Ignore this minus Q2 and minus Q3. Ignore the negative heat branches. Take only the plus ones. Put that in Q given and calculate the work done. And then finally efficiency is work done net by Q given, right? Use this formula. That's how you calculate efficiency for a cycle. Coming to what heat engine is. Heat engine is a very simple device. It takes Q1 heat from a source, rejects Q2 heat. It doesn't use all this Q1 to do work. It uses only some Q1 minus Q2 to do work, right? And the rest of the Q2 it rejects to some sink. So the efficiency formula is I'm sorry, this is wrong. This is Q1, right? So once again, it's work done. Efficiency of a cycle is work done, which is Q1 minus Q2 here, work done by Q given. What is Q given here? Q1, right? So Q1 is what you give. Q1 is what you give. So you will only put Q1 in this formula. So your efficiency is nothing but, for a heat engine, is nothing but 1 minus Q2 by Q1, where Q1 is taken from the source and Q2 is given to the sink. Remember, for a Carnot cycle, only for a Carnot cycle, I can also do this. If source is at a temperature T1, sink is at a temperature T2, then I can also write this as 1 minus T2 by T1, because for a Carnot cycle, Q2 by Q1 is equals to T2 by T1, right? This is for a Carnot cycle. So if I give you what Carnot cycle, if I tell you that this heat engine is a Carnot cycle engine, right, only then you can use this formula. Then you can use either this or this, it will give you the same result. But if it's not a Carnot cycle, if it's not mentioned, then you're supposed to use this. Then you're supposed to use this and not this, right? So heat engine done. Coming to refrigerator, refrigerator is a device which extracts heat from a lower temperature body. This is a temperature T2, right? This is your temperature T2, which is less than T1. So it extracts heat from a lower temperature body and gives it to a higher temperature body. For that, you need to do work on this, right? This will not do work for you. You need to do work to extract heat from a lower temperature surrounding and give it to a higher temperature surrounding, right? So beta, here for a refrigerator you don't have efficiency, you have what is known as beta, which is your coefficient of performance. Coefficient of performance is given by this formula, Q2 by W, right? Q2 is the heat which is extracted into the working substance from the sink. You will put that in the numerator, and denominator will be the work done to do this process, right? What is the work done? So as you can see, W plus Q2 will be Q1, W plus Q2 will be Q1, right? So W is nothing but Q1 minus Q2. So the formula for beta is nothing but Q1 minus Q2, right? And more often than not, you can also replace this by T2 by T1 minus T2, right? If you want maximum coefficient of performance, and these two are maintained at T1 and T2 separately, right? So this was what I had to, and efficiency is always less than 1, as you can see, because Q2 will be less than Q1, right? So this quantity will be positive, this quantity will be positive, so you will subtract this from 1, so efficiency will be less than 1, but beta will always be greater than 1, right? Verify that yourself. So with this, we are done with discussion on this chapter called Thermodynamics, laws of thermodynamics. So practice a lot of problems and get more and more understanding as far as this topic is concerned, because the questions will be based on your understanding of the subject. So I tried my best to cover the most important parts of the chapter. So thanks for watching.